I will begin with a word of prayer. Hem. 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 Dear Father, we thank you again for this opportunity we just have to meet together and study your creation. I just pray you bless this class, Lord. In your name I pray. Amen. So today I need to talk to you about integration by parts. So this is the second. So one of the kind of frustrating things about calculus 2 is it's got a certain kind of jumpiness to it. There's a few different topics we talk about in this course, and they're not always like directly linked. And so there's a part of the course on integration, there's a part of the course on sequences and series, and then there's another part of the course on, like, we have about a week and a half of just basic differential equations. And then there's another about week and a half, 2 weeks of polar coordinates, right? So there are interlinkings between these topics, but you can kind of shuffle them around and put them in different orders. So what I chose to do this semester is to put parametric stuff first, right? Which is sort of me putting my worst foot forward, whatever. So what's done is done. Well, not for you yet. But we now move on to integration. And so integration, I think, is going to be a happier place for you guys because it's more kind of what you've maybe been doing before. So let me just remind you what we already know. In your previous course, you have studied what an antiderivative is. You've been shown the fundamental theorem of calculus part 1, part 2, right? You've done some integrals involving U substitution, all right? And so the next stage in that story, the next chapter in that story, so to speak, is other integration techniques. So other integration techniques, what we're really looking at are programs, what's the word? Maybe algorithms, strategies of educated guessing. The goal is to take a given expression and manipulate it in such a way such that we can find the antiderivative of it, right? So how do you do that? Well, the first way you do it is just with educated guessing. That's what I started the course with. I put a bunch of things on the sideboard, had you guys just write those integrals down. How did you know those? Because you studied differential calculus, right? You know if you differentiate sine, you get cosine, right? So the integral of cosine is what? Sine, right? And so forth. So that's the first thing. You got to know your elementary integrals, the ones we wrote on the sideboard day one, first thing, right? After that, you got to be aware of the technique of U substitution. We'll run into that again and again. But then past that, there's integration by parts is one technique. There are implicit substitutions, which predominantly focuses on what's called the trigonometric substitution. All right, we'll see that. Not today, but later. And then after that, we'll study what's called partial fractions. Partial fractions decomposition is a technique for integrating any rational function. So that's a very general and interesting technique. And that's kind of beyond that. There's sort of exotic substitutions known for particular problems, but that's kind of it. So we have these three major techniques: integration by parts, implicit substitutions, trigonometric and hyperbolic substitutions, what I mean there, and then partial fractions. Those are the three integration strategies we're going to learn. And then, of course, we take those three things and weave them together to solve sort of combined problems. That's where we're going, all right? This is chapter 9 in my notes, all right? So let me get right to it. The basic thing is that we can study the derivative with respect to x of a product of functions, let's say u and v, right? And so what's the product rule say? It says that the derivative of a product is du dx times v plus u times dv dx, right? Okay, fine. So what if I am integrating u times dv dx? What could I replace this integral with? If I solve the product rule above for u dv dx, what do I get? these are functions, they commute, right? I can write the v first and the du dx second if I like. Do you guys agree? Right, so just solving the product rule for u times dv dx gives me the derivative of uv minus v times the derivative of du dx. And so I can trade this integral for this integral. Right? That's just by the product rule. But then we have properties of integration, right? So this is like the integral of d dx of the product of u and v dx minus the integral of v du dx dx, right? Using linearity of the integral. Now we're talking about indefinite integrals. So what's the derivative, what's the integral of a derivative? Can you tell me how the first term, how does this guy right here simplify? So this, if we differentiate and then we integrate, that's just their inverse processes, right? This is the antiderivative of the derivative, so we're just back to uv again. Right? So this formula I've written on the board right now is known as integration by parts. So, yeah. Oh, okay. Now, we could do what? We could like think about canceling the dx's. If we cancel the dx's, then we could think about an integration in u, right? Excuse me, an integration in v on the left-hand side. We think about an integration, I mean, another notation for this would be the following, that this is the integral of u dv is equal to uv minus the integral of v du. All right? Oftentimes this is what's referred to as the integration by parts formula. But there's two kinds of integrations we're interested in, right? Indefinite integrals, in other words, finding the most general antiderivative. Really, it's a set of antiderivatives. Or the other kind of integration we're interested in, definite integrals, right? A definite integral is a number. It describes the signed area under the curve in question, right? So this same bit of calculus gives me the following definite integral formula, right? What if I could put bounds everywhere here, right? How would that change things? The integral from a to b of u dv dx is going to be what? u v evaluated from x equals to a to x equals to b. So we take the difference, right? The difference of the u and the v functions evaluated at b and the u and the v functions evaluated at a. And then we subtract the integral from a to b of v du dx dx. So this is the integration by parts for definite integrals, where this, of course, I mean u of b, v of b minus u of a, v of a as usual, the evaluation of the difference of the upper and the lower. So this is the general result. It's called integration by parts, and now we're going to apply it to solve some integrals. What do you wish was true? What's wishful but wrong thinking? How about this? The integral of f times g dx is just what? Right? This is not true, though, right? So we have to do something else. Just like, same for derivatives, right? Is the derivative of sine the derivative of x times sine, like the derivative of x times the derivative of sine? You know it's not, right? We have to do the product rule. And so integration by parts is the natural analog of the product rule for integrals. Like everything else with integrals, it's a little bit trickier, right? Differentiation's kind of, I think of differentiation being pretty straightforward. Integration usually involves some kind of backwards thinking, right? All right, so I shouldn't have even written, I should probably just erase this from the board before somebody takes it out of context and starts doing this. I mean, if this were true, this course would be much easier, right? But it's not. Okay, so let's look at an example. Integral of x e to the x dx. So in order to do integration by parts, what we want to do is we want to evaluate, we want to identify what is u and what is dv. So I'll do that for you here. This we're going to say is the dv, and this right here we're going to say is the u. So then we've got uv minus the integral of v du. So if u equals x, then du is dx. If dv is e to the x dx, then what's v? E to the x, right? You might think e to the x plus a constant, but there's a reason we don't need to add a constant when we integrate the dv, right? So let's see here, does this work? We got x, e to the x, minus the integral of what is v? E to the x, what's du? dx. Well, I think that's a pretty good trade. We've traded integral of x e to the x, which we didn't know how to do, right? Now for x times e to the x, fine, that's just a function. And integral of e to the x, which is, hey, that's an elementary integral, right? That's something we did on the sideboard already. We know how to do that. And then I add a constant since we're doing an indefinite integral. Let's do another. Integral of x sine of x dx, let's say from 0 to pi over 2. So again, the first order of business is to identify what's the dv, what's the u, all right? So in this one, I'm going to let dv be sine of x dx. I'm going to let u be x. So I go off to the side. I need to tell the reader what I'm doing, right? So I write a little box on the side here that just organizes my thinking. I say, all right, I said u equals x. I said dv is sine x dx. So that means my du is dx. And that means my v is what? I got a minus cosine x. Now, that is correct. And so, okay, well, I'm supposed to do x times minus cosine of x, right? I'm supposed to evaluate that from 0 to pi over 2, and then I'm supposed to subtract the integral of minus cosine of x dx from 0 to pi over 2. I'm going to clean that up a bit. So what we're looking at is minus x cosine of pi over 2 plus 0 cosine of 0 plus the integral from 0 to pi over 2 cosine of x dx. What I did there was I minus minus gives me plus, right? Oh, it should. Thank you. Now, fortunately, that mistake could have been harmless as they go, because what's cosine of pi over 2? Right. I mean, if you wrote x there, I should still take off a point, though, right? You would want me to tell you that, right? No? Oh, okay. All right. Yeah. Cosine of 0 is 1, but that's multiplied by 0. So long story short, the uv term gave us nothing, right? And we're just left with the integral of 0 to pi over 2 of cosine. And what do you expect that to be? Positive, negative, 0? Can you guys tell me without calculating what that should be? I mean, think about the graph of cosine. It starts at 1, drops to 0, between 0 and pi over 2. So I think it should be a positive number, right? Okay, let's calculate it. The antiderivative of cosine is sine, and we evaluate from 0 to pi over 2. Fundamental theorem of calculus, part 2, right? So that is the sine of pi over 2 minus the sine of 0, also known as 1. So this integral is 1. If you start your integration with a definite integral, every step will be a definite integral, unless you make a break and start talking about an indefinite integral, right? You can't start with no bounds and then, like, mid-problem, just add bounds. I will take off points, all right? You have to be consistent. If we start with an indefinite integral, we end with an indefinite integral, right? It's not, you don't start definite and then, like, or start indefinite and then, like, midway add bounds or something, all right? So this is the proper notation. Example 3. I will focus on indefinite integrals because I think every time I do a definite, it takes a bunch more time. And I think you guys will, I don't think people really have much trouble with the definite integrals. Most of what you have to learn is, like, how to actually do the integration by parts, right? So if you're sitting here watching this, there's probably something that you're starting to think, which is, okay, but how are you choosing the u and the v, right? Yeah, I haven't answered that yet. We're just doing it. There really isn't a universal answer to that. The annoying answer that I will give you is, well, you try something, right? So here's one that we didn't know how to do before. Integral of log x dx, right? So, all right, what's my u, what's my v? So let's start to think about the process of choosing u and v. In order for your choice of u and, well, dv to be successful, what do you need to be able to do to dv? You need to be able to find v, right? So our choice of dv has to be something that we can actually anti-differentiate, right? Something that we can actually integrate. I can't choose dv to be something I can't integrate, right? Like, so, I mean, so I really can only pretty much do what I'm about to do, if you think about it. So if integration by parts is going to be successful, it almost has to be this. It's pretty much your only move. So there we go. U equals to natural. I mean, it remains to be seen whether or not it's going to work. What's du here? I'll do the v. V is x. Du is what? 1 over x, so we've got dx over x, right? All right, so I'll write it down symbolically again. This is uv minus the integral of v du. What's that look like here? That would be x log x minus the integral of what was v? X. What was du? Dx over x. Whoa, look at that. The x's, they be canceling. And that's pretty nice, because now we've got x log x minus the integral of dx. What's the integral of dx? X, right. I heard a story once about a professor who he had to give the first test in, like, calculus 2, or maybe the last test in calculus 1, It depends on where you are. Sometimes we'll get the integration by parts in Calculus 1 at some schools. I think NC State's Calculus 1 currently gets through like trig substitution. All right. For example. But, so he gave a test, and part of the test had like integral of dx, right? So that what the professor did is like brought his grandson in after the test and marched him up to the front of class, like a 5-year-old, right? Marched him up to the front of class. He said, "Son, what's the integral of dx?" "X plus a constant, sir." And then he looked at them. He says, "Even a 5-year-old knows it. What's wrong with you guys?" But that's little consolation if you hit the integral of dx on a test and you've never, just for whatever reason, never thought about it. And it's like, what? But yeah, it's x. All right. So, hey, now we know how to integrate log. Yay. All right. Again, I still haven't entirely answered the question of how we're picking u, have I? And I'm never going to. But I will give you a sort of generic strategy. Example 4, integral of inverse sine of x dx. I'm working myself into a corner. Let me stop. So again, I really only have one choice here, right? Because I don't know how to integrate inverse sine, right? We know how to differentiate it. We don't know how to integrate it at the moment. So I pretty much have to make this u, and I pretty much have to make the dx dv. You notice as we're doing this that we don't make the choice of u or the choice of dv in isolation. They're a package deal. You have to declare both, right? Just like u substitution, right? You don't get to just substitute the integrand and ignore the dx. You have to manage the dx as well as the integrand in the u substitution. Same thing there. All right, so anyway, u equal to inverse sine. So what's du? Yeah, I got dx over the square root of 1 minus x squared. Very good. dv is dx, so v is x. Here's my little thought bubble off to the side. So what do I got? I call these the training wheels sometimes. But it's good to put the training wheels on your paper. They help you not make a stupid mistake. Yeah? So, I mean, this step right here, is this necessary? I'd say it's necessary when you're starting, right? Until you're completely bored of writing that, it's necessary. And maybe even then it's still necessary, because it keeps you from making stupid mistakes. Watch me when I'm lecturing. The minute I stop doing this, I'll do something stupid by not doing it. I mean, so I get in a hurry, right? So we have x. I'm putting the x first. Why? It looks nicer. That's it. I just like to write the x before the inverse sign. I mean, technically this is VU, but they commute, right? All right, well, this one's a little bit more interesting than the ones we've hit so far. Now I've got an integral of x dx over the square root of 1 minus x squared. So what do I do with that? How do you deal with this? Let w equal what? So if you don't have a firm grounding in u substitution, you'd be stuck here, right? If you haven't properly studied u substitution anytime recently, it would be a great time to review, because not knowing u substitution, or in this case w substitution, it's going to be a deal breaker. But that's an integral we can solve with just a plain substitution. We substitute w equal to 1 minus x squared. That gives me a dw is minus 2x dx. So therefore x dx is what? Well, minus x dx is what? It's it's dw over 2, right? So I'm gonna take that minus and this x and that dx and trade them for a dw over 2. I mean, I've got a minus, I've got an x, I've got a dx in the original expression, so exchange for dw over 2. We can do that, right? And what's the integral of 1 over the square root of w? 2 times the square root of w. What's the derivative of square root of w? Hey, it's 1 over 2 square root of w. So this anti-differentiates to root w. Have to add my constant. And finally, finishing blow. There you go. Yep. What's the integral of this 1 over the square root?
If you have it over there as dw over 2 square root of w.
But the thing is, ddw of the square root of w is 1 over 2 times the square root of w. So if I want to integrate 1 over twice the square root, it's just square root. I'll do it over here. If I integrate 1 over the square root of w, what is that? This is the integral of w to the minus 1/2 dw, which is w to the minus 1/2 plus 1 divided by minus 1/2 plus 1 plus a constant, right? Which is, right, so that's 2, you're fine. So that half cancels with that too. But I don't look at it that way. I mean, when I see 1 over 2 square root of w, I think, oh, well, that derivative of square root is 1 over twice the square root. So the integral of 1 over 2 square root is just square root. Anyway, I think we'd all come to the boxed equation. If you don't follow my internal thinking and you have your own internal thinking, which gets you to the same point here, I don't mind. I'm not saying you have to do it exactly my way. You just have to do it a way, which shows steps. Okay? All right, we're on example 4 now. Is there any kind of pattern that's emerging for our choices of u and v? I don't know. Let's do another. Oh, I'm sorry. It's mean to the front row. I think I can squeeze example 5 in here. What if we had integral of, say, x squared e to the x dx? Well, this time I'll let my dv be e to the x dx. I'm let dv1 be e to the x. I'll let my u1 be x squared. So dv1 is e to the x. What's v1? E to the x. All right, so integrate by parts. I've got x squared e to the x minus the integral of 2x e to the x dx. Oh, fine. u1 v1 minus the integral of v1 du1 equals x squared e to the x minus the integral of e to the x times 2x dx. I think we're making progress here, right? Because we've traded x squared times e to the x for x times e to the x. We're getting closer to something which is elementary, which is just integral of e to the x, right? So it seems like if we just integrate by parts again, I think we'll have it, right? So let's do it. What we got? Now, this time, I'm going to let me use some color coding here so you can see what I'm doing. I'm going to make the e to the x and dx be my dv2. This one and that one, I'll say dv2 is e to the x dx. And my u2 will be 2x. Right? So that's going to be equal to x squared e to the x, that's still out there, minus, parentheses are your friends, u2 v2 minus the integral of v2 du2. All right, let me scooch this over here a bit. So that's going to give us x squared e to the x minus, big parentheses, what's u2 v2? So du2 is just 2dx. u2 v2 is 2x e to the x minus the integral of e to the x times 2 dx. The parentheses are important, so you don't forget to distribute the minus. A very, very popular error in your next test. Forgetting to distribute this minus. Because you guys have some aversion to putting parentheses where they belong. Like, it really, really bothers me to write something like square root of x plus sine x dx. Like, I don't like that. Doesn't even faze you guys. Like, the thought that maybe there should be like a parentheses here. It's just not even on the, definitely not on your bucket list. I mean, I don't know. You guys are too young to have bucket lists. But you guys don't even watch TV. Anyway. I don't take off points for that anymore. It's too tiring. X squared e to the x minus 2x e to the x plus, what? 2 e to the x plus a constant. There you go. Answer. But isn't that obvious? Right? If somebody came to you and said, hey, I want a function that if I differentiate it, it gives me back x squared times e to the x, you'd be like, huh, I've had calculus 1. I'm a smart guy. The answer is x squared e to the x minus 2x e to the x plus 2e to the x. Oh, and you can add a constant. Said no one ever, right? I mean, this is an interesting technique. It's actually allowing us to derive antiderivatives that would be otherwise inaccessible, right? It would take a very clever person to just rattle this off from guessing, direct guessing, right? You're like, well, I have a phone and Google, so I could just do that, right? I mean, if that's demotivating you from learning this, you know, I'd hate if you were a jogger. You'd be like, you know, working on your training run and then see somebody driving in a car and go, what am I doing? I could have taken the car, right? It's not about the answer. It's about the process. It's about honing your mind, your intellect, your algebraic skill, because you are in an engineering or a science discipline where mathematical language and thinking is valued. And the only way you can really get good at mathematics is to like get into it. And that's what this course is about. So, all right, I'm done with my sermon. Question, how are we picking U and V? Now, when I first taught Calculus 2, students told me this, and as much as it offends me to tell you as a mathematician, I don't know if I'm a mathematician, but I do mostly just think about math, so I guess that might make me a mathematician. I don't know. Whatever. So this offends me, what I'm about to tell you, but I'm telling you because students find it helpful, all right? So choose U via liate. And then this is generally successful. So Here, I'll put it over here so everybody can see it. Liate. This is going in order of preference of choosing u for the integration by parts. Numero uno, log. If there's a log, that's what you're going to make to be u, probably. If there's an inverse function, well then, that's going to be the u. If there's an algebraic function, and there's not, a log or an inverse function, you probably should make the algebraic function the u. If there's no the lia, then we're to trigonometric. If after those fail, if there's a trigonometric, then you probably make the trigonometric function the u. If after all of that's done, then last but least, we use the exponential as our choice of u. Now, the reason this offends me as a mathematician is that these are not mutually exclusive categories. For every logarithm is the inverse function to an exponential, right? And algebraic functions can be inverse functions to other functions. So like, I don't know, these are not mutually exclusive categories. Like, what does this mean? But nevertheless, students find it useful. Let's see how this played out. Example 1. Is there a log? You're like, yes, there's a log. E to the x is e to the log of e to the x, right? There's a log. No, you guys don't do that, right? So, since you're normal people, you don't see a log here. And so what's our choice? All right, log's out. Inverse function? Nope, no inverse function. E to the x is the inverse of log. See, this bothers me. Anyway, so there's no inverse function, quote unquote. Is there an algebraic function? Oh, x is algebraic. That's why we chose, or this is why Liate chooses x to be u here. All right, next up, example 2. Again, no log, no inverse, algebraic. First pick, u equals x. Example 3. Oh, log, finally. U equals log. So we made u equal log, and it worked, didn't it? Example 4. No log, but, oh, look, inverse function. It's even labeled as an inverse function. Can't miss it. That means we make u equal to the inverse function. And in fact, we did that. And modulo calculus 1, you might have forgot. It was safe, right? We did it. Example 5, x squared is an algebraic function, right? So there you went. There it goes. And again, in the next step, we still made the algebraic function the second u, right? So this Liate thing, it's pretty successful. But anyway, so maybe that answers the question that you guys have been about to ask for the past 15 minutes, yeah? Okay. All right. So let's do nastier ones. Because I'd hate for you to get to your homework and then have, like, hey, there was nothing like that in class. All right, well, yeah. See if I can find one. Now, this makes me nervous. I haven't worked this one out before class, so I'm a little bit concerned about this. I'm not sure this is going to go well. There's a chance I won't be able to do this. What example are we on? Example 5?
We're on 6.
Oh, 6. Okay, I can't count. It's a good thing I don't do math for a living. Let's see. Integral of e to the square root of x dx. All right. Well, I definitely don't know how to do a u substitution for this one, right? How do we do this one? I don't know. I guess if I trust in Liate, I should make u equal to what? There's an algebraic function here, right? What's the algebraic function? Square root of x. Oh, but that doesn't, I still have to, it has to be u dv, right? So I don't, actually that's not an algebraic, it's a composition of an exponential with, I think we got to go with exponential. if I trust in Liate, and I don't. But e to the square root of x. So what's du? It's e to the square root of x times 1 over 2 square root of x dx, yeah? And my dv? Well, that's dx, so that's not bad. So this gives us, what do we got? uv. Did it help? Well, I like the x e to the square root of x. I mean, okay, I can write that. This term's never a problem. It's this that we got to worry about. Integral, x, yeah, I don't know. 1 over 2 square root of x e to the square root of x dx. Well, all right, well, that can be simplified. X e to the square root of x minus 1/2 integral of square root of x e to the square root of x dx. Yeah, well, doesn't look like it's making it better, does it? Not really, yeah.
What if, like, at the beginning, then we were the square root of x as x to the 1/2 and brought the 1/2 down?
Oh, can we do that? So we have e to the square root of x is e to the x to the 1/2. But the thing is, there's a parentheses here like that. I mean, if it was the square root of e to the x, that would be a different thing. That would be e to the x to the 1/2, and that would be e to the x over 2. So, you know, actually this integral is a completely legitimate thing to ask any Calculus 1 student. That doesn't require integration techniques. It just requires laws of exponents and a basic u substitution. So I don't think that, but I think you might be in the right direction. Maybe we should try making a substitution before we try integration by parts. All right? So let me erase. How about this? What if we let, what do you guys want I'm going to use a theta. Let theta equal to the square root of x. If I do that, what's d theta equal to? It's going to be dx over 2 root x, right? So what's this integral of e to the square root of x equal to with a theta substitution? So this says what? Dx is equal to 2 square root of x d theta, also known as 2 theta d theta. Hey, I like that. So what this is integral of 2 e to the theta times theta d theta. Now, guess what? We've gone full circle. We're back to 2 times my first example. The first example was the integral of x e to the x. Now we're looking at the integral of theta e to the theta. So we can do integration by parts to solve that, right? So this is 2 times the integral of theta e to the theta d theta. So what I do is I let my e to the theta d theta be dv. I let theta be my u. I get 2 times uv minus integral of v du, which is 2 times theta e to the theta minus the integral of e to the theta d theta. So we get 2 theta e to the theta minus e to the theta plus a constant. And then unsubstituting, that is 2 square root of x e to the square root of x minus e to the square root of x plus a constant. Now, this example that I'm sharing with you right now, example 6, I don't typically do this on the first day of integration by parts, because to me, this is that fourth case I was talking about. We study integration by parts, we study implicit substitutions, we study trigonometric, we study partial fractions, and then at the end of that all, then we combine methods. This is a combined method problem because it's not just straight integration by parts. I had to make a substitution in order to get to an integration by parts problem. So you're like, so why are you covering it today? It's Dr. Sprano's fault. He put it in my mind. He told me he gave a quiz with this, e to the square root of x dx, and 2/3 of his class couldn't do it. So, yeah. Oh, parentheses are my friend. I shouldn't. So yeah, you're right. I should either distribute the 2 through or put parentheses. Yep. Yeah. So anyway, this is Dr. Sprano's. It's all his fault. It's his influence. He put this in my mind to work this problem. So yes.
How did you get from the 2 root x d theta to 2 theta d theta?
Square root of x was equal to theta.
Oh, okay.
Uh-huh. Yep, yep. Oh, I think we know this now, so I'm going to use this board. There is another thing that happens with integration by parts that always drives you guys batty. So I should tell you. I should show you an example. Well, actually, I'm not sure it happens for this one. Let me try it out. I believe we can do this with integration by parts. Sine of the natural log of x dx. All right. So this one, what should we let? I think we have to make sine of the log to be the u, right? So we got all the way to the t. Remember the choice of u, the u has to appear multiplicatively, right? Remember that the integration by parts formula is that the integral of u dv is equal to uv minus the integral of v du. So that u, it has to be sitting out there multiplying the dv. I couldn't make u equal to log x because the log is inside the sign. It's not multiplicative, right? Anyway, that's my dv. So my u was what? My u was sine. What's the derivative of sine of the log of x? Looks like we got cosine of the log of x, yeah? dx over x. All right. And so what's that going to give us? That gives us, looks like it gives us x sine of the natural log of x minus the integral. Oh, something cool happens. Check it out. Like the v and the du, the x's cancel out. See that? So in the v du, this x and that x cancel. And we're just left with cosine of the log of x dx. Okay, so that's kind of, well, it's different, right? At this point, I realize I'm going to have to integrate by parts again. So I'm going to do some window dressing here. I'm going to put some put some ones up here just to keep myself, you know, on the straight and narrow. And up next here, I'm going to say that this is u2. And I'm going to say that that's dv2. So u2 would be cosine of the natural log of x. And dv2 would be dx. So what's du2 is minus the sine of the log of x dx over x. And, well, v2 is x. So I'm going to try integrating by parts again. because I kind of feel like it's gonna go back to where it started. And you might think, well, if it goes back to where it started, how can that help you? Well, let's think about that. Parentheses are my friend, so minus big old parentheses. I'll do it symbolic for a second here. u2 v2 minus integral of v2 du2. X sine log x, still there, minus parentheses. u2 v2 is x cosine log of x minus the integral of, oh, look at it. So this time, fine, I'll write it out, minus the sine of the log of x over x times x dx. So you see what happens here? How many minuses do we got? 1, 2, 3, right? So there's a net minus sign on that integral. So to clean things up here, we've got x times the sine of the natural log of x minus x times the cosine of the natural log of x plus the integral of the sine of the natural log of x dx. It's minus, thank you. Yeah, I just got done explaining why that was minus, only to change my, if that worked out to a plus, that would not be helpful. Yep.
Wait, why is it a minus? 'Cause
Minus times minus times minus is minus.
where's the, oh, you distribute the other minus.
Yeah. Why does this help? Right, so let's give the integral that we're working with a name. Let's call it I. I. What does this say? This says I is equal to x sine of the log of x minus x times the cosine of the log of x, right? Minus I. Via the calculation above. What are we trying to find? Trying to find I. How do you solve for I in this equation? Oh well, I guess I'll move on to the next example. I'm just kidding. Can you solve for I? I'm gonna erase while you guys are thinking. I heard add I to both sides. I. So plus I. I mean, I don't know what notation you want me to use. So that implies that 2I is equal to x sine of the log x minus x cosine of the log x. In other words, the integral of sine of the log x dx is equal to x sine of log x minus x cosine of the natural log of x. And then what should we do because we're calculating an indefinite integral? Plus c, right. Oh, yeah, I can't do math. I go through all that only to not divide by 2. Good job. All right, anyway, there it is. So this is an example of an integral that loops, right? It loops back where it starts, not quite, and then you can solve for the integral algebraically. Yep.
How do you know to add the integral to the sine element dx? So right underneath, after you did the 2I, solve for I, how did you get to that answer right there?
We added I to both sides.
Yeah, so after you add I to both sides, how did you get
I
the integral of sine?
divided by 2. I is the integral of sine.
Oh,
Yeah. Another one that works out like this is the integral of e to the, say, 3x cosine of 4x dx. This one's also a well-known loopy problem. So let me go through. This one has some annoying features like the 4x and the 3x. I have been focusing our attention on other issues, right? This one we're actually going to have to start doing some like implicit u substitutions in order to deal with the 4 and the 3. All right? I don't write those steps down, I just do them. I'll show you what I mean in a second here. This is going to be dv1, here's my u1. I mean, I'm violating Liate, aren't I? It's going to be okay, though. So u1, v1. You guys are like, your allegiance is to Liate, not to me. You reject my methods. I mean, it doesn't seem very nice. Liate never did anything for you. You're like, it helped me not think for integration by parts. That's huge. That's huge. We like not thinking. Let's see here. No, that's not true. du1, 3e to the 3x dx. In contrast, dv1, cosine of 4x dx, integrate that, we get v1 is 1/4 sine of 4x, right? That's the, I'm not explaining why it's 1/4, okay? We do this kind of u equals 1/4 4x substitution in our head. If you need to write it down, but I'm not going to write that down. I'm just going to write that. All right? Now, so this gives us 1/4 e to the 3x sine of 4x minus the integral of 1/4 sine of 4x du. Why did I put it? You guys are probably talking about why there's a 2 there. Why is there a 2 there? The short answer is women. I'm not sure I'm allowed to make that joke anymore, though. Let's see here. Let's see here. So do you know, fall of man? Who was it that ate the fruit first? Remember? All right. Let's see here. 3 to the 3x dx. Just saying. Have you ever heard a pastor say that Adam ate the fruit as an act of self-sacrifice? He knew that it would mean death, but he wanted to honor his woman, so he just went along with her. Have you ever heard this sermon? Every once in a while, you'll find a misguided pastor who will say this. Although their number are decreasing. It's like the ultimate misinterpretation, I think. But it's like the how to offend feminists with the Bible 101. Let's see here, e to 3x. I don't believe that, to be clear. Jokes have to be, you can't just say a joke anymore. You have to say, oh, and that was a joke. So be careful. I probably should just edit this out at this point. I think we're that far in. Let's see here. Oh, look. So now we've got e to the 3x sine of 4x. What are we going to do? Right, so we're going to focus our attention here on this piece. We're going to make we'll let this thing be our dv2. I'll let this e to the 3x be my u2.